The sky just gave scientists a new mystery. Fresh data from the James Webb Space Telescope changed what many thought about the interstellar visitor named 3I Atlas. They show a different mix of gases than common comets. The result raises serious questions. But here's the twist: before astronomers even finished tracing its path, the James Webb data suggested something no one wanted to admit. If this isn't a normal comet, then what is it? How we found it. On July 1, 2025, the Atlas Survey Telescope found a moving object in the sky. The survey is run by the Asteroid Terrestrial Impact Last Alert System team and uses wide-field cameras from Haleakala in Hawaii and additional units in Chile. The Discovery team reported the object and gave it the temporary tag Atlas. The orbit calculations quickly showed a hyperbolic path, which means the object came from outside the solar system. Astronomers assigned it the interstellar label 3I Atlas when those early orbits did not match a bound path. Observers from Cerro Pacun in Chile, Mauna Kea in Hawaii, and sites in Namibia and South Africa confirmed the track. Early photometry showed a faint coma in some images. The small glow suggested volatile material was present, which raised the possibility that the object is a comet rather than a bare rock. The discovery set off a rapid follow-up by many teams, including the European Southern Observatory, Gemini Observatory, Lowell Observatory, and NASA teams. Telescopes measured speed and incoming direction. The object was fast, moving at tens of kilometers per second relative to the Sun, which matched interstellar velocity expectations. Accurate orbit models used observations from multiple nights to rule out a bound orbit. Within days, the object was labeled interstellar, and many groups prepared instruments to watch it as it moved toward the inner solar system. Scientists also tracked its future path. NASA calculations show that 3I Atlas will reach perihelion near October 30 this year, at about 1.4 astronomical units from the Sun. The closest it will come to Earth is near 1.8 astronomical units, so it poses no impact risk. These numbers helped scientists plan observations for before and after the closest solar pass. On August 6, the James Webb Space Telescope used NIR-SPEC, its near-infrared spectrograph, to observe the object. The instrument breaks light into a spectrum and reveals molecular emission features that identify gases. The Webb team, led by Martin Cordiner at NASA Goddard, recorded spectra from 0.6 to 5.3 microns. The data were processed, and the team released a preprint that listed detailed measurements. Webb observed the comet at about 3.32 astronomical units from the Sun while the object was inbound. Early Webb images showed a brighter coma on the sun-facing side, which suggested sunlight was driving activity. That pattern is common for comets when the Sun heats their surface and causes gases to leave the nucleus. The Webb observations gave a clean set of infrared fingerprints that other telescopes could then compare. This early coordinated effort set the stage for a rapidly growing dataset that included space and ground assets. But here's where things took a strange turn, because Webb didn't just confirm what astronomers expected. It revealed something unusual, something almost unsettling about this comet's chemistry. What exactly did Webb uncover? What Webb saw? The James Webb Space Telescope observed 3I Atlas on August 6, 2025, using the near-infrared spectrograph. Webb recorded light from roughly 0.6 to 5.3 microns. Those wavelengths reveal molecules that glow in the infrared. The dataset came from a team led by Martin Cordiner at the National Aeronautics and Space Administration Goddard Space Flight Center and collaborators at several universities and institutes. Webb observed the object when it was about 3.32 astronomical units from the Sun. The spectrum was clear enough to identify multiple molecular bands and to measure relative strengths. The most notable result is a coma dominated by carbon dioxide. The infrared bands for carbon dioxide are strong and easy to see. The Webb team measured a carbon dioxide to water ratio near 8.0, with an uncertainty close to 1.0. That value is far above the typical ratios reported for most comets at the same distance. Water vapor appears in the spectrum at lower levels. Carbon monoxide is present but weaker than carbon dioxide. The spectrum also shows the sulfur-bearing molecule OCS at detectable levels. Small grains of water ice mixed with darker dust appear in the data as broad features and a characteristic infrared slope. Webb did more than identify the molecules. The instrument provided spatial detail across the coma. The data show stronger emission on the sun-facing side of the nucleus. That pattern matches what happens when sunlight heats the surface and causes ice to vaporize. By measuring brightness at different positions, the team derived production rates for each species. Production rates tell how many molecules escape per second. These numbers allow scientists to quantify how active the surface is at the observed distance. A high carbon dioxide fraction raises several possible explanations. One is that the body formed in a region with abundant carbon dioxide ice. Protoplanetary disks have temperature zones where certain ices freeze out, so formation location matters for composition. Another possibility is surface processing. Long exposure to cosmic rays and interstellar radiation can alter surface layers and remove some volatile molecules. If surface layers are lost or changed, the active layer that releases gas when heated may show a different mix than the deep interior. A third idea is thermal shielding. A dust or crust layer could limit heating to shallow regions, so more volatile carbon dioxide at shallower depths could dominate release while water stays locked deeper. The Webb paper compared 3I Atlas to known solar system comets. One comparison mentioned is Comet C 2016R2, Pan-STARRS, which has an unusual carbon-rich chemistry. Even with such comparisons, 3I Atlas sits well outside the normal distribution of carbon dioxide to water ratios. The team provided numerical uncertainties and band strengths so other researchers can test their own models against the published values. Those numbers permit direct comparison to Jupiter family comets, long-period comets, and known outliers. SPRX, the spectrophotometer for the history of the universe, epoch of reionization and ICE's explorer, observed the object across a different time window from August 7 to August 15. SPRX covers complementary infrared bands and provides independent confirmation of the molecular signatures. When two instruments record similar patterns, the case for a real detection strengthens. The combined Webb and SPRX data form a more complete picture of the infrared behavior during early August and reduce the chance that a single instrument artifact explains the result. Using Webb production rates, modelers can estimate the fraction of the surface that must be active to produce the measured output. Those estimates depend on assumptions about surface temperature, sunlight incidence angle, and grain properties. The models produce ranges for active area and volatile inventory. As the object moves closer to the sun, these numbers can change if new vents open or if fresh material becomes exposed. Observers will update models as new measurements arrive to refine the active area estimates. Infrared spectral slopes and specific features also reveal grain sizes and the dust-to-gas ratio in the coma. Webb data point to small icy grains mixed with darker refractory dust. That mix affects how the coma scatters light and how the tail will form. The presence of water ice grains at 3.32 astronomical units indicates that some volatile material can survive at this distance, while carbon dioxide dominates the gas output. Grain properties inferred from the spectrum help link gas detections to the visible appearance seen by optical telescopes. The Webb preprint lists named authors from institutions in North America and Europe, including the National Aeronautics and Space Administration Goddard Space Flight Center and the Catholic University of America. The team released production numbers and uncertainties so that other observatories can compare their measurements. These values will anchor follow-up studies and guide planning for radio, optical, and ultraviolet campaigns as the object approaches perihelion. Planned follow-up includes radio arrays such as the Atacama Large Millimeter-Submillimeter Array, the Northern Extended Millimeter Array, and the Hubble Space Telescope. Ground observatories like the Very Large Telescope and Gemini South will monitor changes. These coordinated campaigns will refine composition and gas velocity measurements and timing. But here's where the story takes a sharp turn. Because while Webb mapped the big picture, the ground teams began uncovering details that didn't fit expectations. What strange truth was hiding inside 3I Atlas?